Good morning, everyone. Thank you, Paul, for your introduction. The subject that I'd like to talk about today is related to image condition. And this image condition in particular exploits wavefield directionality in order to address artifacts that appear in reverse time migration in full waveform version. The idea here is to use space-time vector fields that have information about wavefield directionality and use a simple operation between these space-time vector fields from source and receiver wavefields in order to form image free of artifacts. Let me show you first how conventional imaging works. In this animation here, I'm showing a schematic plot of source and receiver wavefield. Source wavefield is represented in blue color, and receiver wavefield is represented in red color. And you can see that the source wavefield has the source location at the origin, and the receiver location is at the x equals 5 kilometers on the surface. And if we extrapolate both of these wavefields, we can image a reflector at some depth, in this case 2.5 kilometers of depth. Let me properly address here the wavefields, because as you all know, the wavefields are in function of space and time. So let me add here the time axis, which in this case is scaled by the velocity. So I'm making the units consistent here in all axes. And later on I'll show why this is important to show the time axis is scaled by the velocity. So in this case we can see the full character, the space-time character of those wavefields. And you can see that the only location where the source and receiver wavefields they coexist is the reflection location. So this is the operational principle behind the conventional image condition. However, the velocity that I'm using here is constant. Realistic velocity models have a lot of heterogeneities, which cause backscattering reflections during the wavefield extrapolation process. So let me show you what happens when these velocity contrasts they are in place. Here I'm showing these schematic source and receiver wavefields separated now, and the dashed lines. And the dashed line is representing the backscattering reflections. If you overlay both of these wavefields in order to get an image condition, we can see here that when you have backscattering, the wavefields coexist not only at the reflector location but also along the reflection path. And this forms an artifact in numerical images, as I'll show next. With this simple experiment, with only one source and one receiver, located respectively by the blue point and the red point. And here I'm including a velocity contrast at 2 kilometers of depth in order to generate these backscattering reflections. In the conventional image condition, outputs the following image. Here, we can notice basically two patterns in this image. The first one is an ellipse-shaped pattern, which represents all possible reflector locations. But also we get this artifact here, this low number artifact, which is exactly it's caused by the correlation of the wavefield along the reflection path due to these backscattering reflections. And some people have addressed the problem of the backscattering artifacts using wavefield directionality. For example, pointing vectors, which describe the energy flux direction using vectors, and also wavefield separation up and downgoing parts. I want to go one step further here and overcome some disadvantages in these methods, in pointing vectors and wavefield separation methods for imaging, using the energy norm. The energy norm is defined this way. The first term inside this summation is related to the kinetic energy of the wavefield, And the second term is related to the potential energy of the wave field. And that's why it's called the energy norm, because it contains both kinetic and potential terms. An image, a wave field image, we deal with source and receiver wave field. Therefore, the norm does not directly help us. We need something else. We need, in this case, an inner product that takes two wave fields and applies a scalar and outputs a scalar quantity in the end. So, based on the norm, we can define this inner product with two arbitrary wave fields. And notice here that we have some symmetry in these two terms here. In the first term with the time derivatives and the second term with the spatial derivatives. We can rearrange these terms in a vector form, as I can show here. And actually, this inner product is a dot product between vectors that are built from each wave field. So these vectors, as you can see, they contain the spatial gradient of the wave field, and also contain the time derivative scaled by the slowness. And this has everything to do with the time axis scaled by the velocity that I showed earlier. So therefore, the velocity is the scaling factor between the time dimension and space dimension. There is a compact notation for these vectors, which I'm showing here, this box operator. And this is used in wave theory and spatial relativity, commonly. Therefore, if we evaluate the Zener product in each spatial location, we can define also an image condition. And here I'm highlighting the color convention again, blue for source wave field and red for receiver wave field, since now we're talking about wave field imaging. Okay, I want to emphasize here the difference between pointing vectors, which is relatively known by the industry, and these energy vectors that are defined here. The first interesting aspect is that the pointing vectors, although it contains also spatial and time derivatives, they only contain 3 components. And for these energy vectors, they have 4 components, which means exactly the 3 components from the spatial dimension plus an additional component from the time dimension. And also, in order for you to perform imaging for the pointing vectors, you need first to estimate angle between the pointing vectors in each location, in each spatial location and time step. And after that, you need to design a weight function in order to select the range of angles that you are interested in. In the case for the energy vector, I will show next, you only need to apply dot product between these vectors in order to form an image free of undesired events. Since we all have seen the difference between the pointing vectors and the energy vectors, let us visualize these energy vectors in the same schematic plot that I showed earlier. So again, I'm showing a source and receiver wave fields, ray path that represented this wave field, and then I'm showing here exactly these energy vectors. And you can all see that they concisely show the propagation of these ray paths through space and time. If we overlay these vectors from source and receiver wave field, we obtain the following plot. And if we perform imaging with these vectors, for the backscattering event in particular, we're not attenuating it quite yet. Because as you can see, for the backscattering events, the vectors here are collinear, they are not orthogonal yet. Therefore, how the image will look like if you use exactly this image condition? It will look like this. So as you can see, as expected, we're not attenuating the backscattering artifact yet. And also, we attenuate normal incidence reflection angles here. So, in order to properly use this image condition to remove undesired events, not only these normal incidence reflectors, we need to modify these vectors in order to make them orthogonal to each other and apply the image condition, the dot product between these vectors. Therefore, we need to modify one of the box operators, applying a scaling factor that compensates for these angles that we want to attenuate. In this case, I'm saying that theta subscript c means exactly the reflection angle that we want to attenuate. And then we can perform this modifying image condition in order to attenuate selective reflection angle. So let us see a couple of examples using 30 degrees, if you want to attenuate 30 degrees reflection angles, and in the bottom if you want to attenuate 45 degrees reflection angles. And then, in this image you can see that the locations where this reflection angle is occurring, the reflector is being attenuated. An interesting goal is to use the scaling factor for the backscattering case. In this case, the cosine of 2 theta c will be equal to -1, and then the scaling factor will be simply the -1 scalar. And then the image condition will be the dot product between these vectors with this modified box operator on either one of the wavefield vectors. Let me show you here how the vectors there are in this schematic plot. As you can see here, if you apply this modification into the receiver wavefield energy vectors, we can see that they are really orthogonal. And that's why I'm using this animation here to rotate. And then you can all see, like in every perspective, that these angles are really orthogonal for the backscattering events. And there are no orthogonal for the reflection event, as you can see here in the center. Let us see for the numerical experiment. The same numerical experiment as before, only one source and one receiver. And here I'm showing the evolution of the application of the image condition over time. So you can properly see that this image condition, compared to the conventional image, really attenuates the backscattering artifact. And then, when the stack over time is done, we obtain the following images. A very common approach to attenuate these artifacts, and that is used by the industry, is to apply a Laplacian operator on the conventional image, as I'm showing here on the top. And as you can notice, those images are very similar to each other, and this has a reason. This can be explained theoretically, that the Laplacian image condition and the energy image condition that I defined here, they are actually theoretical equivalent, and this is shown earlier by Duma in 2010. I'd like to address here the practical difference between these two image conditions. For the Laplacian operator, as you all know, it's a positive image filtering of the backscattering artifact, and it only attenuates the backscattering artifact itself. You cannot modify this image condition to attenuate any other reflection angles. However, for the energy image condition, it's a pre-image process. It's applied before stacking over time, and attenuates any selective reflection angle. And I'll show you later that this is important, and this has actually an application for full waveform inversion. Now, for more complex models, like the Seismic model, we can visualize how the image will look like for one single experiment, for a shot. And you can see here the shot configuration, the source location here, by this blue dot on the surface, and a line of receivers represented by this red line. And then, if we're performing wavefield image on this, using a conventional image condition, as expected, we obtain a lot of backscattering artifacts. If we use the energy image condition, however, we attenuated these artifacts, and we can see the reflectors that for the conventional image condition, they are maxed by the low even number of artifacts. Okay, now I'm showing here the whole velocity model because for the following slide I'm going to show the stack image over experiment. And you can notice that this model is quite complex and it has this south boundary which, as expected, will generate a lot of artifacts in the conventional image. And here you barely see the reflectors underneath the south boundary. If you use the energy image condition, then you obtain this result. Okay, now is the part of the talk where I'll explain that the flexibility of this image condition in attenuate other reflection angles rather than backscattering, it's quite useful. We can use this for an application for every applied to select, instead of remove the backscattering artifact, instead of remove the event that corresponds to wave field that propagates along the same ray path, we want to select these events and remove the reflections from other angles since they are undesired for the initial stage of the full waveform version because they do not contain any tomographic information. Let me show you here the two special cases for this image condition. And before stacking over time, this image condition consists of a dot product between these energy vectors. And if you want to attenuate normal incidence, and if we transform this dot product into the Fourier domain, that's why I use the tildes here, you notice that the amplitude changes with respect to reflection angle. And also for the image, for the dot product that attenuates the backscattering artifacts. And for the dot product that attenuates the backscattering artifact, this is an expression very similar to the Laplacian expression that is shown earlier by John and Son. So as you can see here, there's an interesting property between these image conditions. If we remove all the effects of, in this case, omega squared by prior integration over time of source and receiver data, and after stacking over time multiplied by the velocity squared, we can, in this case, remove the effects of all of these terms and have the effect only on the term that is depending on the reflection angle. In this case, this sine squared of theta and cosine squared of theta. And as you can see, sine squared of theta and cosine squared of theta, if you sum these dot products, we end up in the conventional image in the Fourier domain. So, because of this interesting property, I call this image condition as complementary. And I'm going to exploit this complementary property between these image conditions for the application in full waveform version. Let me show you individually each one of these functions when you remove all of the effects from the other terms. For the dot product that attenuates the normal incidence angle, as you probably can see, it attenuates the reflection angle equals to 0 and has maximum amplitude for 9 degrees. This would be in some way used in order to, as an image condition to compute the gradient of the full waveform version method. However, we have a very broad range of angles, of reflection angles here that we want to eliminate. We want to make this narrower, as you can see here. In order to do this, an interesting filtering technique is to apply an exponential function that decays the most for angles far from 9 degrees. And fortunately, the other dot product, the one that attenuates the backscattering events, indicates how far a reflection angle is from 9 degrees. And combining these two dot products, we can use this filtering technique here, using the backscattering dot product in our argument of an exponential function and then being applied on the other dot product that attenuates in our instance. And therefore, in the end, we obtain this function here with respect to reflection angles. And you can see here that we achieved our goal to have a narrow range of angles here near to 9 degrees, which corresponded to the terms that we want to emphasize in the scientific part of the full waveform version. I'm going to show next a couple of numerical experiments, very simple ones. Here I'm only using one source and one receiver, and for the initial velocity I'm incremented by 20%. And the goal here is to obtain only the direct wave correlation. However, as we have increment in velocity, the initial velocity, we're going to side escape and then also obtain a correlation, a reflection shape correlation that you can see here for conventional full waveform version. And the idea is to eliminate this reflection shape correlation based on the filter technique that I showed earlier. And this is exactly the result that you obtain using the filtering procedure. Then I'm going to use another experiment now with no increment in velocity. And the expectation here, I'm adding now a free surface. The expectation here is to have the direct wave correlation and the correlation from the reflection, from the backscattering reflection from the free surface. However, we also obtain a little shade through factor due to the free surface, which is not intended here. If you use conventional full waveform version, you can notice this ellipse-shaped reflector that we do not want, we want to avoid. Using the filtering technique, we can properly attenuate this. Now, I'm going to make this more difficult, use an incrementing velocity in the same model that uses the free surface. So this is basically a combination of the two experiments that I showed earlier. And here, because you have, besides the free surface, you also have incremental velocity, you're going to have all sorts of crosstalk artifacts in your full waveform version gradient. And as before, the result that we want is only the correlation along the direct wave path and the reflection path from the free surface. Conventional full waveform version gives this result, which, as I said before, has a lot of crosstalk artifacts that we want to avoid. Using the filtering technique, we can suppress most of them and emphasize the tomographic term in the direct wave path. Okay, summarizing, my presentation, I showed an image condition based on the energy norm that exploits wavefield directionality using space-time vector fields. And a simple operation between these space-time vector fields leads to an image. And we can use this to attenuate backscattering artifacts in reverse time migration. And also, if we explore the flexibility of this image condition and attenuate other angles, we can also use this as an application for full waveform version in order to attenuate crosstalk artifacts. And not only that, the image condition here is applying on the acoustic wavefield imaging, but it is based on the energy norm. The energy norm is quite general, and therefore the energy norm can be defined not only for acoustic wavefield, but also for elastic wavefield. And the theme of my presentation this afternoon is going to be exactly developing an elastic image condition based on the energy norm that exploits as well wavefield directionality in order to suppress undesired effects. Thank you all for your presence here.